Welcome back, everyone.
Okay, you cannot be seen.
So go stand, look over her shoulder.
Or here.
Oh,
Or stand right here. Okay, yeah.
you know what? This is weird.
Yeah, look over.
This is a lot better. Okay, welcome back, everyone. We are very pleased to have Radmila Sazdanovic here to tell us about linear pairings on two-dimensional cobordisms and generalizations of the Deligne category. I'm excited. So thank you for coming.
Thank you for inviting me. Thank you, everyone, for coming in whatever shape or form you were able to do so. It's a pleasure to actually give a live talk, right? I mean, live, whatever. Everyone knows what I mean. Yeah, so welcome, everyone. So please feel free to interrupt me if you don't hear me, don't understand something, or for whatever reason. I will be, so for those of you who were here in the morning, the talk was announced. So this will be another example of something related to the universal construction. So I hope that's going to become clear. I'll give you a tour. There's going to be just a little bit of overlap where I'm referring to the parts of universal construction that I need. But apart from that, this is the overview. So as announced in the title, right, I will be talking about the Deligne category, and again, I'm going to go into more details as the talk progresses. So depending on how familiar you are with either part of the story, details are coming. I just want to give a broad overview. So the Deligne category that I'm denoting by rep of S sub t interpolates between the categories of finite dimensional representations of symmetric groups and elements. The good thing about it, or the best thing about it, it has a diagrammatic representation. You can actually do so or visualize that through so-called partition category, and then the Deligne category is just the Karoubi envelope of the additive closure of this partition category. So where does this relate to cobordisms and such? Well, Combs and other people have used the diagrammatic interpretation to sort of relate to this diagrammatic interpretation, and in that way, the partition category and the Deligne category with two-dimensional cobordisms. And very, very informally, just to give you a flavor of how that works, if you know the diagrammatics for the partition, it's sort of like some sort of tangle-looking type thing, right? Just no crossings. So the way to go from the partitions to the cobordisms, and again, there'll be details on all of this, is that you just thicken the partition and then you get a surface with boundary, and that's how you kind of go through cobordisms. And from cobordisms, you just look at the boundary and then forget the genus and you forget all the closed components. Khovanov's universal construction in 2 dimensions, basically, again, if you take whatever happened and specialize in 2 dimensions, basically looks at 2-dimensional cobordisms and has an extra input. That was this function that sort of tells you how to evaluate these closed components. So if you have something just floating around, if you have a closed surface there, you know this function tells you how to evaluate those closed components. So the result here in this talk, in this work, is basically that you can match these 2 approaches, right? So you can find an interpretation of the partition category in the Deligne category, where this input function that can be also viewed as a sequence, infinite sequence of values that are assigned to each, let's say, surface of a particular genus. When it's a constant sequence, that's when you recover the Deligne category and the quotients and so on and so on. But if you don't look at this constant sequence, then you can take any other sequence. That's how you get the generalizations. Any questions? Right, so we have several moving pieces here. We have the Deligne category and partition category that are soon going to become diagrammatic. And then we have various cobordism categories that I'm going to go through and explain what we're doing with them. And I'm going to be contrasting that with the universal construction, because that sort of gives us a way to kind of bring these 2 together. Okay. So, but before I do that, again, maybe you have seen various low-dimensional examples in Khovanov's talk, the beginning of the conference. I have even a simpler example, right? So if you think about various algebras that I hope at least some of you are familiar with, you can kind of think of a group algebra of a symmetric group, CSN, where we just denote the transposition by, the cross between I and I plus first strand. Then you can get the Hankel algebra just by kind of considering the crossing, right? You can have left over right or right over left. Again, I'm not putting relations. It's not going to be relevant or necessary for the rest of the talk. And then, of course, there's the famous temporary Lieb algebra, right? That's generated by elements that look like this, where instead of a crossing, you have a so-called return, right? The cup and a cap here. And of course, there's like a bunch of relations, right, that I'm not mentioning. And usually you sort of evaluate the circle at 2 or q plus 1 over q or so. There's various versions of it. So one thing that we did early on is actually create some sort of diagrammatics that actually relates to these two types of polynomials, and in general with one variable polynomial ring. So why am I stating this is because it's a kind of very curious result, and it's a result that predates this work that I'm going to talk about now, where you look at classes of orthogonal one variable polynomials, and then you say, okay, well, how am I defining orthogonal polynomials? Well, I have some sort of inner product, right? That here I have an inner product for Chebyshev polynomials of a second kind. Here I have an inner product for Hermite polynomials. And then what you can do, you sort of say, okay, Chebyshev polynomials are orthogonal with respect to this inner product. Hermite polynomials are orthogonal with respect to this inner product. But what I can do, I can take just the monomials, x to the n and x to the m, and use this inner product to create kind of a pairing between them, right? And sort of say, well, what do I get when I plug in x to the n and x to the m instead of f of x and g of x, right? And with a little bit of help of high school mathematics, you actually get that this is a Catalan number that's n plus m divided by 2 Catalan numbers. So you have m and m have to have the same parity. And you say, okay, great, right? Catalan numbers count among other things, right? Count the number of crossingless matchings. So we kind of have a diagrammatics in mind that comes from temporary diagrams right here already. And then if you're bored by this, I'm going to challenge you to kind of think about for like one slide, what kind of diagrammatics will correspond to the double factorial, right? We have n plus m minus 1, and then we skip 2, or half factorial, however people like to call it. Okay, so anyways, this is where the bilinear form comes into the play. These are various ways in which you can take something very simple, one variable polynomial, or like a ring of one variable polynomials with integer coefficients, take a bilinear form on them, and then try to categorify them. So this is going to be a very steep transition from this slide to the next slide, where I'm hiding the whole paper that's maybe 2-3 years old, and even more. When you think about not publishing. So what we can do in the approach that's somewhat similar, it has the same flavor as the approaches that we're going to be using today, we can actually categorify these Chebyshev polynomials. So what do? We're actually going to consider diagrams of this type. Again, I've turned them left to right here just because I'm used to them this way. They can have left returns, right returns, and certain number of through strands, which is similar to temporary diagrammatics, except that, and this is one way in which they're differing from things that we'll be doing now, we're basically not allowing things like isotopy. So we're going to evaluate the circle to 0. And then every through strand, like maybe this one that has more than one critical point when projected to the x-axis, is also 0. And then if you have a return, it can have only one critical point. So something that goes like this is 0. So you can kind of think about, okay, well, great. That means that when I forget about topology, right, instead of the Jones polynomial, I get the Chebyshev polynomials. It's not quite like that, but that's like a cute way, I think, of saying it. So again, I'm hiding a lot under the rug. I'm just sort of saying, like, this is the diagrammatics that we're using. What we're actually going to do, we're going to consider this as a Chebyshev diagrammatically defined algebra. And then we're going to consider certain classes of modules on top of that, algebra, projective, standard, and so on. And then even on top of that, we're actually going to consider a monoidal category of bounded complexes of projective modules over this algebra up to chain homotopies. And once you compute the gross unique ring of this category, so what I did not say is this monoidal category that you get. The algebra product is just given by placing things on top of each other. The monoidal structure is given by placing them parallel to each other. When you compute the gross unique ring, it turns out that up to all of these conditions, we've got rid of exactly enough things that we got the Z of X as a ring, isomorphic to the gross unique ring of this category. And in this assignment, we get that what I did not say here, that the projective modules correspond to the monomials. So nth projective module correspond to the x to the n, and the nth Chebyshev polynomial corresponds to so-called nth standard module. Again, you don't have to know this. I just kind of want to give you a flavor of these things. And again, this is the relation that sort of comes out of the projective resolutions of standard modules.
Where do these like Chebyshev modules, are they come up naturally?
So they come up naturally, and this is like things that I'm not claiming that I know much about, but it's like a categorical analogy. So you have projective and standard modules in the sense that they appear in these categories. Yes. So yes, they do come up naturally, at least to, like in my point of view. Yes. Okay. So, but I did have Hermite polynomial. So what's counted by double factorial n plus n minus 1? So there you actually can consider diagrams like this. Again, we're not allowing isotopy. All of the circles are evaluated to 0. But here we can sort of say, okay, all crossings are allowed, and then we can kind of progressively get rid of them. You allow only crossings between through strands, and then you don't allow crossings between through strands. And so sort of the game that you're playing is kind of similar, where projective modules would correspond to, in this decategorification by taking gross unique ring, projective modules would correspond to the monomials, and then the standard modules, so-called big standard modules, correspond to Hermite polynomials. Again, I hope that this inspires you to look at other polynomials, not necessarily not polynomials. And again, in the light of the previous talk, that these that there's maybe a lot that can be explored, and there's a lot of examples that we can come up using using these approaches. But again, like one thing that sort of distinguishes these things that I've just talked about is that we are basically not allowing isotopies. It's not naturally topological thing, right? Okay, so now let's go to partition category, the link categories, and then cobordisms. So a partition category that I'm denoting by P sub AT can be considered over a ring or a field K. We're going to fix one element of it. And then it can be thought of as an extension of a partition algebra in kind of similar ways, where you can kind of think about tangles as an algebra or tangles as a category. So objects are non-negative integers, shown here on the bottom. And then I have a morphism, let's say from 4 points to 6 points, where the points on top are denoted by primes. They're going to be given by linear combinations of these decompositions of a collection of n plus m points, right? That are denoted here. So again, for example, a partition that sort of puts 1 prime, 1 and 3, 2, 4, 6, and 6 prime, so 2, 4, and 6 prime, and 2 prime, 4 prime can be denoted this way. What I wanted to emphasize here, again, it's not going to create trouble, but there's like more than one possible diagrammatic representation for each partition, and I've just picked another one where instead of connecting 1 prime and 1, I'm connecting 1 prime and 3. Now let's kind of consider this one and this other elements. So this one is a morphism from 4 points to 6 points. This is from 6 points to 5 points. The way that we're going to define the composition or the operation here is given by concatenating diagrams. So I'm going to place B on top of A, and again, I need the number of points to match here. And then what happens is that I can get these floating components here that are not part of the original description. So that's where the choice of the element of your ring or a field comes into the play. That's how we're going to evaluate. So every closed floating component is going to be contributing a t to the image. So I simplify my diagram and I get t squared times this new diagram C. Okay, so that's a partition category. What's the Deligne category? Again, for simplicity, let's say that I have a field of characteristics 0. And then I already mentioned the Deligne category is the Karoubi envelope of the additive closure of the partition category. And then here are some of the facts that we're going to need.
What's the Karoubi envelope?
You allow all the formal sums and then you kill all of the idempotents that you sort of need. It's yeah. So what's important here is that depending on the value of t here, when this category is going to have a non-trivial ideal given by so-called negligible morphisms. And again, I'm going to talk more about that. So let's leave it for now. But basically, well, maybe not. Let's talk about it. So in order to know what a negligible morphism, you need to sort of first consider the trace on this category. And again, when you look at these diagrammatics, all that you're going to do, you're going to connect 1' and 1, all the corresponding points. You're going to connect them, and then depending on how many closed components you get, the trace is going to be t to the r here. So it's going to be t to the power of the number of components. And then the morphism is negligible if there exists, if you fix one element, and then if you can find any other element such that when you compose them, you get that the trace is 0, you sort of get rid of those ones. So this is basically important because we want to get a bilinear form that's non-degenerate. We don't want the pairings to be trivial. And then, of course, what's really important is that the quotient of the Deligne category by this ideal is actually the same as the module, the category of modules of Sn. Okay. So just a quick review of the universal construction. So again, I'm going to state everything here in dimension n, but for the purposes of this talk, think about COP2. Tensor category oriented n-dimensional cobordisms. Objects are oriented closed n-1 dimensional manifolds. I'm denoting them by n. The morphisms are going to be 1 dimensional higher. I'm considering them up to diffeomorphism, of course, relative boundary. And again, the morphism between n1 and n2 is going to have in a boundary n1 and n2 up to orientation. You need to change orientational 1. Then, of course, the TQFT is something that takes cob n as an input and then sends it into the appropriate algebraic category. So that's kind of where you sort of see, oh, I'm evaluating somehow. I mean, just roughly. But basically, we can send it either to vector spaces over a field or maybe projective modules over a commutative ring. So let's sort of see what are we going to do here. I mean, again, this is due to Khovanov. So we're going to come up with this function alpha that works on morphisms. So it's in dimension n. So you're going to assign to each m, you're going to assign some value in your field. And again, this is a function of classes, right? Diffeomorphism classes. So if m is diffeomorphic to m prime, they get assigned the same value. And this function needs to be multiplicative on m's. So if I have a disjoint union of m1 and m2, what alpha assigns to them is a product of the values on constituents. Now let's sort of go 1 dimension lower and see what happens with n's. So again, if n is a closed oriented n-1 dimensional manifold, in the universal construction, the way that we start with this, we're going to start with assigning a free R module with the basis given by the symbols of these manifolds that have n in the boundary. Okay, so again, FR, the sensor free of n, is generated by all manifolds that have n in the boundary. And then what do we
M up to a different morphism?
up to the diffeomorphism always, yes. And then again, I think Khovanov mentioned that. I don't think I have it in slides. If there's an orientation thing, you actually have to enhance it with an evolution. It's going to take care of the change of orientation, but we don't have to worry about it here. But that's a good question, yeah. So now what we can do, we can actually define a bilinear form on this free of n by using the very natural thing where if you have M1 that has n in the boundary, you have M2 that has n in the boundary, well, you flip the orientation of this one and you concatenate them, and then what you're going to get is a closed surface, right, of some genus. Okay, but I know what to do with that. I can use my function alpha and evaluate it, right? So I can say the value of this form applied to M1 and M2 is actually what the function alpha assigns to this resulting thing.
So if construction, if you're not on surfaces, then it might depend on a diffeomorphism.
Exactly, exactly.
Then does your cobordism remember the diffeomorphism of the boundary?
It's relative boundaries. You have to fix. It has to fix
So
the
you
boundary.
fix,
Yeah. So in higher dimensions, it's always relative boundary. Yeah, I said. Yeah. Mhm.
Okay, sorry, I didn't.
No. Thank you. So please feel free to interrupt me. Okay. So then the state space of n for this particular evaluation alpha is going to be the quotient of this free module n module the kernel of this bilinear form. And then, of course, if you just randomly pick your alpha, you're probably going to have this alpha band have infinite rank. That's usually harder to deal with. So we prefer the one that has finite rank. So again, examples are scarce, right? But soon I'm going to actually show when there's a theorem that sort of says when that's the case. Actually, so this is just for completeness. Khovanov talked about it. All I want to sort of, maybe let me just emphasize that this map, when it's on n-1 dimensional manifolds, is usually injective over the field, but it's rarely surjective. And again, surjectivity comes from the existence of a neck cutting relation. But again, if you have a neck cutting relation, then you get a TQFT. And that's when you actually get that this alpha is multiplicative on n-1 dimensional manifolds too. Otherwise, it's not. Okay, and it's factorial and so on and so on. So let me specialize to the universal construction in 2D. Okay, so what happens in 2D? Everything depends on just the number of circles, right? That's one-dimensional manifold. So I'm just going to denote, instead of having free of capital N, I'm just going to note as FR of n, where n denotes the number of circles. And then what are the things that sort of have these circles in the boundary? Well, it's just something that looks like this. Like if it's one circle, you have genus 0, genus 1, genus 2, and so on. So when you think about this free of n, it has a basis that's given by symbols of closed surfaces of genus G, like one for each G. And then again, what does universal construction do? It assigns some alpha of m to each cobordism. And sorry, this alpha of m, you can kind of say alpha as G, right? Sorry that I did not change the notation. And again, this alpha is multiplicative on the diffeomorphism classes of cobordisms. Okay, now how do we, again, let's just sort of mimic, we get the bilinear form on this free of n, given by, again, if S prime and Sn both have the same number of circles in their boundary, I'm going to concatenate them and assign, and the value of this bilinear form is going to be whatever alpha assigns to it. And alpha is always determined just by the genus of the resulting surface. So then the state space of n circles is basically just the quotient by the kernel of the bilinear form. And then this is just bookkeeping. This invariant alpha, that's like a function, can be now encoded by this infinite sequence that just sort of says alpha I denotes the value that's assigned to the, or alpha G, it's just the value that's assigned to a genus G surface. Okay, so here's my example. Let's do things for just one circle, right? So the A1 or the alpha of S1 is spanned by all of the things that look like this, right? You have one circle in the boundary and you have some genus. Okay, now let's describe the Billionaire form. What am I going to do? I'm going to take one of these and I'm going to put another one, change the orientation, glue them together and get the value. So again, I'm sorry, the picture is kind of, I did not repeat the picture, but the picture is up here, right? For example, when I glue something that has S0 and something that has S2, and I'm sorry that my things are moving here. And we're going to get basically something of genus 2. So we're assigning alpha 2 to it. So what we can do, we can collect these into a matrix, so-called Hankel Matrix. And then what happens is that you can do that, of course, for any number of circles. But basically what happens then is that this state space A of 1 is going to be K to the n quotient out by the kernel of this Hankel matrix. If it's going to be a finite codimension, then we know that there's going to exist some number of these VIs, let's say R of them, that span all of A01. And in that case, what does that tell you? That basically tells you, let's say if R is 2, right? If you actually stop here, what that means is that any higher Vn is going to be able to be expressed as some combination of V0, V1, and V2. So basically that gives us a skein relation, gives us a way to get rid of all R plus 1 and higher dimensional handles and express them in terms of lower dimensional handles. Okay, and then the good news or the great news is the theorem due to Kronecker and Khovanov, although I don't think they've explicitly collaborated, that sort of says that if you have a field, then the following are equivalent. If the dimension of a space of one circle or M circles, if they're finite, well, that's equivalent to having this Z alpha of T be a rational function. So the sequence of values that you're assigning to your surfaces of genus G basically corresponds to a rational function. So now we have a very explicit condition on these alphas that we can use to do things. So now we're going to take this whole setup and we're going to extend it to something that I'm denoting by Cobb alpha. And again, that's going to be like a two-dimensional topological theory where every closed-oriented surface G evaluates to alpha G. But in order to get this Deligne category, we're actually going to look at the constant alpha, the one that assigns the same thing to each genus. So, and they're all treated the same. So this Cobb alpha, again, is going to have objects non-negative integers, and morphisms are just going to be our linear combinations of cobordisms that are quotiented out by this relation that we have. So these cobordism categories basically fit into the following kind of diagram. So we're starting with COB2, and then we get to R COB2, and again, for simplicity, you can just take R to be a field. So we're just in R COB2, we're just allowing linear combinations of morphisms. Okay. Now this next one is the interesting one. So F2 is the moment where you take into account the sequence or the function alpha, right? That's where you sort of evaluate all closed components according to this function alpha or sequence alpha. So this is your Cobb alpha prime. Now, what are the morphisms in this Cobb alpha prime? Well, they're just given by the basis of cobordisms that have no closed components, right? Because we'll get rid of them. Because we evaluated like we did in partition category or we did in these first one-dimensional examples. Now, the next thing is sort of the algebraic thing. So this F3 basically says, I did not say what the negligible morphisms are, but we sort of say we're going to kill all the negligible morphisms. That in turn gives us our Billionaire form to be non-degenerate. And then finally, we get to the additive Karoubi closure that I'm denoting by Cobb alpha. And I think to denote this, know that this F4 is actually a fully faithful functor. Again. Okay, so this is what's happening just with cobordisms, right? And this extra evaluation. So how are we going to find these Deligne categories? Well, we're actually going to define additionally these two categories here. So that's the rest of the talk. And I just want to sort of point out that these vertical maps are just taking the Karoubi closures, and these two maps are just taking quotients with negligible morphisms. So basically, again, now you still see how this idea from the universal construction gets kind of paired with this approach to get the partition and coborism categories. So in order to do that, I want to go back to the relation that's due to Combs and Savage and Ostrich and many other people, and sort of say, well, okay, how do I bring back the partition category or the diagrammatic partition category? So this is my kind of more explicit kind of picture or something. So if I have a cobordism, what do? I forget about all of these closed components, and I also forget about the genus of anything here. And then I basically look at the boundary. I look at the boundary of what's left. And again, if I have the partition, I'm just going to take in the graph. So what sort of Combs figured out is that if you mod out the cobordism category, if you mod out the cobordism category, if you mod out the cobordism category by relations that sort of get rid of the handles and evaluate the circle at T, which is our chosen element, you basically get the partition category. Okay, so in kind of more details, like if you have a morphism X, that's let's say this guy, you can associate a partition that I'm denoting by P of X, that again depends on the number of points here and here, by sort of like looking at the remaining closed components, sort of and kind of just taking the boundary like of these guys. Again, you can pick one or the other right here. But what I want to do, I want to extend this sort of pictorial relation. I want to extend it to a functor between categories. And in order to do that, well, on objects, it's just the identity. And then on morphisms, well, what do we have to do? We kind of have to take into account this CL of X, which is just the number of closed components that we have here. In this case, that's 3. So then we're going to have T raised to that number. And then we just take this partition that I've just described above. And of course, everything is extended to our linear combinations. Okay, so what's the relation? Let's go back to the universal construction. What's the relation what we have done now to what was before? So this space A of alpha is actually just the direct sum of the state spaces A sub alpha on N, where N ranges from 0 to like infinity from the universal construction. And that basically gives us a natural representation of this category Cobb alpha prime. And again, to an element N in Cobb alpha prime, you assign this module A alpha of N, and to, I apologize for a mistake, to a cobordism, I associate like a module map, right? Because that's what usually happens. That sends A alpha N to A alpha M. Well, how do I get that? Well, I'll just evaluate X that's capped off in various ways. And so on. Okay. Finally, how do negligible morphisms look like? Well, you know, if this is your morphism, I'm hiding all the complexity here. You basically just connect the top circles with the corresponding bottom circles, and you evaluate that one. So the trace map would be given depending on this function alpha and what it assigns to this particular image. So again, back to the universal construction. In the universal construction, we were modding out by the kernel of the bilinear form. the equivalent here is modding out by the negligible morphisms. Okay, something to notice that's just a useful thing when you're proving things, and I think it's not hard to see. If you're actually looking at the home space in this Cobb alpha between N and M, it actually can be realized by kind of taking all of the bottom circles and kind of pulling them up here. And then you evaluate, it's the same as the home between 0 and N plus M. And again, that's the state space for N plus M circles here. So basically you have the representation of the kernel of the bilinear form that sort of helps us kind of see. It just illustrates this isomorphism here. Okay, so just a little bit more on coborisms and partitions. Again, in these categories, Cobb alpha prime and Cobb alpha, if we focus on a constant function alpha. So the signs are chosen element T, no matter what the genus is, we actually get, again, the handle removal and this evaluation holds. So basically what that gives us is that we can squeeze the partition category between Cobb alpha prime and Cobb alpha. And maybe just let me remind you, so going from Cobb alpha prime to Cobb alpha is given by quotienting out by the negligible morphisms. So again, this partition category is actually just here kind of in the middle. And again, this functor comes from the Combs observation, and it's essentially in their paper. And again, this is just due to the analogy that I just like sort of hopefully pointed out for you between the quotienting out by the kernel of the bilinear form and the negligible morphisms. Okay, so how do I get now a generalization? Can I still see this? So this is the partition category. How do I get the Deligne category? Well, I can start with this functor f double prime of T. And then again, this is the algebra part. You take the additive closure, you pass to the Karoubi envelope. And it turns out that it gives you a functor that I'm going to denote by f sub T that's going to be sending the Deligne category into the Karoubian additive closure of Cobb alpha. And again, this is just given by taking the corresponding quotient by negligible morphisms on both sides. I don't know, actually, I don't remember whether I said it here or later. The order in which the closures and the quotients are taken doesn't matter in this case, but in general, it could be relevant. So basically what we get here is that for this particular choice of alpha, when it's constant, we recover the Deligne category or the quotient of the Deligne category by the negligible morphisms. But again, if you take a more general alpha, that's where the generalizations come from. And again, following the theorem by Khovanov, if you pick a sequence that gives you rational functions, then you know the morphism spaces are finite dimensional. Okay, so now the question, now there's the fun part, right? So this is kind of straightforward, right? But we are getting the quotients of the Deligne category, right? So how are we going to get the Deligne category itself? Well, maybe let's kind of go back and kind of think about just a little bit about the correspondence between, I don't have a pretty picture, I'm sorry about it. So when you think about the diagrammatics for the partition category and the cobordisms, there's much more versatility on the cobordism side, right? Because we have the closed floating components and we also have the genus of everything. So those are like the things that we were not taking into account. And also, again, we were taking these quotients because they were natural. So now what happens when we fix a field and we fix a rational function? So I know that my morphism spaces are going to be finite dimensional. So let me take like a closer look into how does this function look like. So I have a numerator and a denominator. And let's sort of say that the corresponding degrees, maximal degrees are n and m, and let's denote by k the maximal degree of n plus m, n plus 1 and m. So in particular, what it means is that the denominator has some form like this, right? It's capital T, it's my formal variable to some power of m. So now if we go back and look at the universal construction, right, what this formula here gives us when we combine everything, it's going to give us that in the space A of 1 of just one circle, we're going to have the following formula, right? When we take the quotient, I'm going to have x to some k, where k is again this maximal here, and the powers will go all the way to k minus m. And then this variable x actually corresponds to a torus with just one circle in its boundary. So it's a genus 1 generator of the state sum of one circle, free space of one circle. Well, this thing is actually our skein relation, right? If you kind of go back to what I was talking about, we're going to have a finite number of generators, and anything with more than this many handles will be expressed in terms of linear combination of lower dimensional handles. Okay, so maybe another thing that I did not sort of emphasize is that the multiplication in the space A alpha of one circle is given by the Pan's cobordism, which is just a natural choice for it. Okay, so how do I get these generalized Deligne categories? So these are things that we sort of had before, right? So we have COB2, linear combinations of morphisms, evaluation here, quotient by negligible morphisms, and then we had the additive Karoubi closure. So if we take as an input this rational alpha and this COB alpha prime that we already had, again, in this COB alpha prime, we have all but closed components are still there. Closed components were evaluated to some alpha k, but these home spaces between n and m are infinite dimensional unless you have a trivial case where you have no points on top and the bottom. So again, infinite dimensional is not the setting where we want to be. And we know that the basis elements are the diffeomorphism classes relative boundary of all coborisms without closed components. And we know in further that they're in bijection with these decompositions of n plus 10 points, basically. But then what we need to take care of now is the genus, right? Because we're getting rid of it now, but now it does play a role. So now we have to additionally keep track of the genus of each closed component. Okay, so what changes? So we're going to get like a new category that I'm denoting by P COB alpha, which has same objects as COB alpha prime, but morphisms are different. So the morphisms, again, we're going to take all the morphisms in COB alpha prime, and we're going to quotient out by the skein relation. And again, what that means is that we're going to get something finite dimensional, number one. But also we're going to get that sort of, we can count things differently now. So the combinatorics is changing a little bit. So how can we describe, or what's the this nice description of the diffeomorphism classes of these cobordisms? Well, again, let's look back. We have everything that we had before that describes the partition. So I have the partitions, the elements of the set D sub n sub m, but I need to kind of even filter it or enhance it, however you want to say, with less than k. That just sort of means that that we're no longer going to be counting just partitions, but we're going to have weighted partitions. Okay, so basically they're going to be labeled, and they're going to be labeled by a number from 0 to k minus 1 that corresponds to the thing that's being lost once you got from coborisms to partitions. So it's going to be the genus or the number of handles in the coborism. Okay, so again, how do I now go back, right? So before I had the coborism X and I assigned a P of X to it plus number of components. So now if I give you a partition P, that's that has an additional declaration that's a non-negative integer. How I'm going to recover the cobordism? Well, I'm going to get the cobordism that we had before that just comes from that partition without a weight. And then this weight is going to tell me how many handles do I need to add. So basically, I'm sort of trying to mimic or recover the information there. Of course, there are things that we need to check right here, right? Because everything works well on the level of diagrams. We need to actually check that this chain relation plays well with the evaluation with the function alpha. And that's not hard to check. And you need to check that there's no additional relations that appear. Because again, we have all the relations that we need, and more relations would make things collapse further, and that's not good. So now, again, when we think about all of the weighted partitions that, again, I'm denoting by the mn less than equal to k, when we convert them to cobordisms, well, they now actually determine all of the whole com space between n and m that's finite dimensional. So the statement that we can make is that this com space in this p cob alpha has a basis given by this cobordisms assigned to partitions p that I'm denoting by p of x over all the partitions here. Com spaces are finite dimensional. And then again, if we work over a field and our function is rational, now we can actually fit in another cobordism category in our chain of categories, this p cob alpha, that again kind of makes this chain finer, right? It fits between cob alpha prime and cob alpha. Okay, and now our work is done because again, this p cob alpha, again, when alpha is constant, it recovers the partition category. For any other alpha, it generalizes it. As before, if you choose k, then that sort of tells you what the dimension of the Hom space is in p gob alpha. And again, that's the same in like partition category. The size of a Hom space does not depend on the evaluation t. It depends only on the diagrams. But in this case, this is given by the number of weighted partitions. That's like the Bell number for tens of combinatorics. K is this maximum between, it depends on the rational function, and it's the maximum between the degree of the numerator plus 1 and the degree of the denominator.
Okay.
It just basically gives you the shape of the skein relation, the maximal power of the skein relation, if you wish. But anyways, if k is equal to 1, then there's no weights, right? So that's just the number of partitions here. K greater 1 is number of weighted partitions, and then just the algebra final step to get from p cob alpha to the analog Deligne category, take the additive Karoubi closure, and that's when the p cob alpha with a k. So here's my summary. So the commutative diagram that I've promised in the beginning now looks like this. Again, the things that sort of come from the cobordisms, this is what we sort of started with various linearizations, evaluations of cobordism category. And then we sort of enriched it with these categories, p cob alpha and p cob alpha here. Right, and then just to kind of bring everything back together, the chain that we had in the beginning that takes the cobordism category into the Deligne category, into the quotients of the Deligne category, by the negligible morphism now generalizes to this red sequence of cobordism categories. Again, they depend on alpha, where we go from p cob to p cob with a k and then to cob alpha. And again, that works for any sequence L with rational power series. So this generalization, the generalization works for everything, right? But this sequence, we can only get it for rational functions. And then again, last but not least, I'm sure I've said it at least 5 times so far, but if we stick to constant series, that of course corresponds to this rational function, we recover the original setup of the partition category and the Deligne category. Okay, so that's it. If you want to look further into these generalized Deligne categories, there's a longish and beautiful paper by Khovanov, Ostrick, and Kononoff, where they take a deeper look or deeper dive into what happens for various rational functions. And in particular, if you specialize, one theorem that's actually particularly interesting and kind of nice to think about. If you have a field of characteristic 0, and then you take a constant function, alpha, so then basically the space A of n is a vector space whose dimension is the nth Catalan number, and then the basis is given by crossing mismatching. So I hope that kind of ties it back to the whole thing. But you can think of other ones, right? There's like the one that sort of assigns like a t, let's say, to the genus 0 surface, right? That bounds the disk, and then 0 to everything else, right? There's like many things that you can kind of consider here. But again, there's much more work to be done. As you know, nothing is known in higher dimensions for universal constructions or any these generalizations. Adding defects, whatever that means. And then, of course, you've heard about the most recent application that's to automata and formal languages. So that would be all. Any questions?
Oh, sorry.
I
Any questions?
feel like I should stand up now, but I probably shouldn't.
Sorry that this is before your work, but when you were defining the Deligne category, at some point you had S-tensor categories representation of Sn modulo Jn, but the negligible morphism is the same as KSN1. What is Jn in this case? Like, I'm just imagining, like, if I'm working over basic representation very book, right? Like the representations, finite dimensional representations, modulo mod nothing is K joined S modules. So what's Jn? Is like the most basic example.
Something that has no floating things, no matter what you compose it with.
We don't ask it. I'm just confused.
Okay. So negligible morphisms are in general, again, we need to, the way that these things tie together is that, again, if you have a pairing that's trivial, that's not good, right? You want to have a big kernel, right? So these negligible morphism, quotienting out by the negligible morphisms sort of corresponds to quotienting out by the kernel of the form. So in general, the definition of a negligible morphism is if you compose it with anything else and you get the trace to be 0, then it's negligible and you should forget about it. So you only keep things that no matter what you compose them with, you don't get a 0. Or so-called negligible morphisms, or at least Khovanov calls them negligible morphisms. Right? Yeah.
I believe there's coffee in the be back in half an hour.
Yep, right.
We'll switch the view to English.
Yeah, so for remote people, we thought,
They
realized. it was
probably
silly
cannot
to,
hear you.
Remote people, we realized it was kind of silly to have two separate Zoom links for the coffee and for this room. So ignore all that about a separate Zoom link. If you want to talk to anyone in the coffee room, just stay on or join the Zoom again. Maybe send that email out too or something.